Now we will be going over the cost minimization problem from the discipline of economics. So this is an economics concept. And the idea is the following. It is to find the cheapest way to produce, in this case, 1,000 units, where we are given the following technology. Q, the output, equals f of k comma L. So our production function uses as inputs capital and labor, where the technology is given by 10 times the square root of k times L. So we are given this example, and also we are also told that the wage rate, the rental rate of labor is $16, and the rental rate of capital is $9. So let's first make sense of this problem. What is the meaning of this? And let me just go ahead and change my marker color. So we have this production function, which actually, let me first highlight this. This is the technology we are using. The function f is described like this: 10 times the square root of k times L. So k represent the machines, machine hours, I should say. L represent the labor hours. Combining them together, machine hours and labor hours, we can produce whatever it is that we are producing, right? Just as an example, just to make sense of this function, suppose that we have three different scenarios. Consider these scenarios. All I'm doing is trying to make sure that everybody understands what is the meaning of this technology. So if hypothetically, so this is my first scenario, if hypothetically we had 4 units of machines, and L were, actually let me just do it next to it, L were 1 hour of labor and 4 machine hours. Combining these, we would have produced Q equals 10 times the square root of K is equal to 4, L is equal to 1, multiplying them out, 4 times 1 is 4, square root of 4 is a 2, 10 times 2 is 20. So we would have produced 20 units, hypothetically, if we were to use 4 machine hours and 1 labor hours combined. That would have given us 20 units of output as this company. Now compare this with another scenario where, alternatively, what happens if I were to combine 2 machine hours with 2 labor hours? Well, our technology would give us that this would have been equal to 10 times square root of 2 times 2. Not surprisingly, 2 times 2 is 4. Square root of 4 is a 2. 2 times 10 is 20 units as well. So it's kind of giving us flexibility in terms of, if your goal is to produce 20 units, so far we have found 2 different ways of doing it. Either I can combine my machinery, my technology, I should say. My technology enables me to accomplish that in at least 2 different ways. Either I can combine 4 machine hours and 1 labor hour, and those combined will give me 20 units of output, or alternatively I can combine 2 machine hours with 2 labor hours, and again I would come up with the same output. Let me yet give you an alternative way, and by now you guys are probably guessing how that's gonna happen, but think about what would have happened if I combined 1 capital hour, machine hours, with 4 labor hours. Well, the technology I'm using will tell me that, well, 10 times capital is 1, times labor is 4 labor hours. 1 times 4 is 4, square root of 4 is 2, 2 times 10 is 20 units again. So wow, so I have quite a lot of flexibility. If my goal were to produce 20 units, I have at least 3 alternatives that I found, and be assured there is an infinite array of ways to produce those 20 units. But pretend for a minute that these are the 3 available alternatives in front of us, right? So these are the 3 alternatives. Let me make note of that. 3 alternatives. You are the manager and you have the 3 alternatives of producing 20 units. Which of these 3 alternatives would you pick? Would you like to produce 20 units by combining 4 machine hours with 1 labor hour? Or would you rather prefer to combine 2 machine hours with 2 labor hours, or 1 machine hour with 4 labor hours to come up with those 20 units? So how will we decide? Decision. It's a managerial decision that needs to be made. So how are you going to decide which of these 3 alternatives is the best? What do we mean by the best? I think it's clear that from an economic perspective, the best is noticing that these 3 alternatives ultimately lead to the same outcome. The best alternative is the one which minimizes cost. Does that make sense? Because in 3 of these scenarios, output is the same. It must be that the process, the alternative, which is the cheapest one, is the one that we should be choosing. So our decision in terms of which one to pick should be the one which is cheapest. Now, in our particular case, because it seems rental rate of machines is cheaper than labor hours, right? So clearly R is less than W. W, remember, is the wage. It represents wage. So it is the price of labor versus R represent rental rate of machines, right? R standing for rent, renting the machines. You can think of financing, borrowing money from the bank to have some lease agreements and leasing the machines as well as other supplies that we need, right? So because rental rate of machines is cheaper than the wage, hourly wage, we might say that of the 3 alternatives, the one which uses less labor and more machines is the desirable outcome, right? So therefore, by just looking at these 3 alternatives in front of me, it seems natural that this is the one that I want to implement. The third one is the cheapest one. Indeed, if I were to calculate cost for each one, let me calculate cost quickly for each of these 3 alternatives, right? So let's start with the cheapest one. 4 units of labor and 1 unit of capital. Oh, sorry. This is the most expensive one. My bad. We should use more machines. More machines, because machines is cheaper, right? And less labor. My bad. All right, let's start with the most expensive one. So using 4 units of labor and one unit of machines. So the 1 unit of machine, each unit of machine will cost me $9. Plus the 4 units of labor, each hour is $16. So the cost of this one would be 64 plus 9, $73. Let me just go ahead and put a $sign in front of it. And I claim this is the most expensive one. Let's compare it with the other 2. Let's go to the second cheapest one, this one, where we use 2 units of capital times the rental rate of capital is 9, 2 units of labor, the rental rate of labor is $16. And as a result, 32 plus 18, that's $50. This is decidedly cheaper than the third alternative. But I claim that there's yet a cheapest way, which is the very first alternative. Let's quickly check. So 4 units of capital times $9 per unit hour, and 1 hour of labor. Each hour is $16. Now 4 times 9 is 36, and 1 times 16 is 16. Okay, I messed up somewhere. Where did I mess up? 32 plus, no, that's correct. 36 plus 16 is $52. Okay, let me check what's going on here. Upon inspection, I just realized that I fell into the same trap that I was trying to avoid, right? Trying to urge you not to fall into. It turns out that, so let me just go ahead and highlight it. This is the cheapest option. Quite counterintuitive, right? So you might say, wait a second, isn't capital the cheapest of the two inputs? Yes, it is. But at the same time, I realize that as I substitute more and more capital to replace labor, it turns out that the total number of units of input increases. So for instance, here in the first alternative, 4 plus 1 in total, there are 5 units of input. Versus in the second alternative, even though we use a little bit more labor than we are supposed to, in total there is less input. So the problem in this sense, it's not obvious. The solution is not obvious at all, right? So technically we are feeling that we should be using less as much capital as we can, but at the same time we are aware of the fact that as we use more and more capital, it's becoming less and less efficient, and it's causing us some trouble as well. So my guess would have been that if we were given a chance, so the optimal allocation would have been somewhere in between those two options. So I bet that if I were to choose capital around 3, for instance, and an appropriate level of labor, which will give, for instance, let me just go ahead and I think this is a good mind experiment. So a fourth alternative, how about I use 3 units of capital and labor, because I want the product to be 4, I think I need 4/3. Let's check this quantity. I claim this quantity will be even better than the 50. Hopefully this time my prediction will be correct. So check this out. So quantity, let's figure out first if the quantity gives us the same answer. So 10 times the square root of 3 times 4/3. The 3's cancel. Square root of 4 is 2. 2 times 10 is indeed 20 units. So far, we are successful. Now, let's have a look at the cost of all this. So, each unit of capital will cost us $9. So, 3 units times $9 each, plus 4/3 units of labor, and each one will cost us $16. Now, when you multiply these out, 3 times 9 is 27, plus 16 times 4 is 64, 64 over 3. Now 64 over 3, I have a calculator in front of me. That gives me 64 divided by 3 is equal to 21.33. So 20 plus 27, that gives 21.33 plus 27. Long behold, it gives me $48.33. Even better than this one, the second option. But how can we be sure this is the answer? Are we sure that there's no better way? So that's the method that we're going to introduce right now. This is the whole point of what we call as constraint optimization. So cost minimization falls into that family of optimization problems known as constraint optimization. And the idea is the following. Indeed, we are trying to this is our objective function that we're trying to optimize in this particular example. Sorry, this is the constraint, not the objective. Sorry, my bad. This is the constraint. The objective function is the cost function, right? The cost function that we're trying to minimize. So long behold, the problem can be translated into the following fashion. And now let's try to go ahead and solve the actual problem, right? So the problem is this. We want to minimize. So this is the actual cost minimization problem now. Cost minimization problem. The problem states the following. If you want to minimize the cost of producing a certain amount, in our particular case, $9 for each unit of capital plus $16 for each unit of labor. Keep changing capital and labor such that this quantity is minimized, subject to the fact that the output you want is 1,000 units. Okay, I just gave this hypothetical example just to have a good understanding, but now we can attempt bigger numbers. We can obviously use our method that I'm about to introduce to solve this simpler problem as well, but now let's go ahead and do that. So to optimize 12, so we want to make sure that 1200 is actually the Q. Oh, sorry, not 1200. I mean, it was, 1000, my bad. So 1000. So Q is equal to, 1000 units. But Q is given as 10 square root K times L. That's it. So our goal is to minimize. So this is the objective function. Let's go ahead and write that out. So this is our objective function, and this is the constraint. In fact, there is two other constraints, which is obvious that constraints. The two invisible constraints are the following. It might be a good idea to write them out as well. We want to make sure that capital and labor are all the time positive, right? You can't have negative hours of machine input or negative hours of labor input, right? That's the celebrated cost minimization problem. So what I did is I applied it to this particular problem where we are told that we want to produce 1,000 units of output, where the cost of rental rate of capital is $9, and the wage rate, the hourly rate of labor is $16. So how do we do this? It's based on something called the Lagrangian. Okay, so let me just go ahead and introduce that concept. So first we construct what is called as the Lagrangian. And the Lagrangian of this problem is the following. All you do is you rewrite the objective function, which in this case 9k plus 16l, and you add to that a penalty, which is lambda, times the constraint. But in this case, what we can do is we can move that 1,000 to the right hand side. Does that make sense? So, and that will give us 10 square root k times l minus 1,000. There you go. So now I can close the parentheses. And that's pretty much it. So this is our Lagrangian. So now at this step, we need to do pretty much three things. The third one is extremely simple. But the two things that we need to do is the following. We need to take the partial derivative of this function with respect to k and set it equal to 0. We'll do the same thing with respect to L and set it equal to 0. And the third one, it turns out, is a very simple. It turns out that we need to also take the partial derivative of this function with respect to lambda as well. But it turns out that this is just the initial constraint that we were given. So that one is easy to handle. So when you set this equal to 0, it turns out that this gives us 10 square root k times L minus 1,000, which is basically our original given equation. So namely 1,000 is equal to 10 times square root k times L. All right, so that one was easy. The first two, how do we do it? First, we take the partial derivative of our Lagrangian. So this is lambda in as a script, the partial derivative of Lagrangian with respect to k, which basically tells you that just imagine k is the variable, L is a fixed, and lambda is a fixed thing. So all you do, wherever there's a k in your expression, let me just mark them in yellow color. So wherever you see a k in your expression, these are the variable, and these are the expressions for which you need to take the derivative. The rest is basically to be treated as constant, and because they are constant, their derivative will be 0. So first, let's take the derivative of 9k, which is just a 9. This one is 0, so let's move on to the next term. Lambda times 10 times square root kl. Well, square root of something, it's 1 over 2 square root of that expression times the square root of inside, so by the chain rule. So that's simply plus what? Plus 10 lambda, square root of the inside is L, and then we have 2 square root KL. That's it. We could have done the same thing for the labor, and let me just go ahead and do that. 16 plus 10 lambda k over 2 KL. That's pretty much it. Now life is pretty easy. What we can do is we can substitute these expressions into each other. There's usually a simpler way to do it. I can first move those 9 and 16 onto one side of the expression. Let me just go ahead and do that for both of them. So what happens is minus 9 is equal to 10 lambda L over, I won't even bother changing any the rest of the expression because it turns out that it will simplify immediately, right? K over 2KL. Now what we can do is we can take the ratio of those two equations. When I take the ratios, the 10s will cancel, the lambdas will cancel, the 2's cancel here, even the square root KL's cancel. As you can see, things simplify enormously. What's left on the left hand side is 9 over 16, and what's left on the right hand side is L over K. Do you guys see that? So from those two, let me just scroll it up a little bit. So by combining these two results, what we found is yet another equation. 9 over 16 is equal to L over K. Or if you want, that will tell you that L is equal to 9K over 16. Now we can go ahead and substitute this amount onto this equation here, onto the third equation. Remember, huh? So we have those three equations and three unknowns, namely K, L, and lambda. Lambda already vanished, so we don't have to worry about lambda. So equation 1 and 2, when I take them the ratio of each other, lambda will disappear automatically, and that's always how you solve these equations. Then you will get an equation in terms of L and K from the first two equations, and the third equation had another expression in terms of L and K. You should be able to solve them simultaneously. Let's just go ahead and solve them simultaneously now. So we have, well, first of all, the 10 and the 1000, the zeros cancel, so we have 100 on the left hand side and square root K times L on the right hand side, and then I can further take the square of both sides. So therefore, on the left hand side we have 10,000 after squaring the 100, and on the right hand side the square root is disappeared, it's K times L, but the L I'm replacing it with what I have here, right? So K times 9K over 16, and now I almost have a home run. 9 over 16 K squared. So on the left hand side we have 10,000, on the right hand side 9 over 16 K squared. I can just go ahead and move that 16 and 9 also to the left hand side. So therefore what happens is 16 times 10,000 all divided by 9 is equal to K squared. And now I can go ahead and take the square root of both sides of this expression. So the square root of 16 is a 4, the square root of 10,000 is 100, the square root of 9 is a 3, and the square root of K squared is just a K. So long behold, K as a result is equal to 400 over 3. And if you want, you can just write an approximate answer, which I won't even bother, right? It's approximately 133 units of capital. But now we can go back, and labor as a result comes out, because labor is given as 9 times K all divided by 16, 9 times K all divided by 16, 9 times, now that K is 400 over 3 all divided by 16, that's equal to the 9 and the 3 will vanish, they cancel, there's a 3 left here, the 16 and the 400, there's a 25, 3 times 25 is a 75. So we are saying that this is the optimal allocations, the cost minimizing amounts for K and L. 400 over 3 units of capital and 75 units of labor is the one which will minimize the cost of producing 1000 units of output. So let's go all the way up. The question was to find the cheapest way to produce 1000 units of output, given that this is the technology we use and the fact that this is the cost of labor and this is the cost of capital. Now, what is that cost? We can easily calculate it. So therefore, the cost, minimum cost is simply equal to 9 times K star plus 16 times L star at the now. These are the minimum amounts. 9 times K star is 400 divided by 3. 16 times L is 75. So the 3's cancel. There's a 3 here. 3 times 400 is 1200. And if you have a calculator in front of you, 16 times 75, 16 times 100 is 1600. 3/4 of 1600 is 1200 again. And long behold, the minimum cost of producing 1000 units, given the production technology that we have, is $2,400. One can apply the similar technique to calculate this initial motivational problem that I gave you. And actually, let's check if the ratios match, right? So if they were, I now started to think that this might be the optimal ratio. Remember that the optimal ratio came out as 9K over 16 for L, right? Let's see what it will come out as. Does it give us 9K over 16? Does it give us L? 9 times 3 is 27 over 16. No, it's not. So therefore, it means that there's even a better way. So this is not the optimal way, actually. There's yet a cheaper way to produce those 20 units, but I leave it to you as an exercise. So we solved the main problem, which was to find the cheapest way to produce 1,000 units, given that the rental rate of capital is as it is, and the rental rate or the hourly rate of labor is as it is, again 16 in that case, and 9 in the case of capital. And that's pretty much how we would solve this cost minimization problem. Hope you enjoyed it. In the next video, I would like to provide how Excel would do that very same calculation.